Hello legends, I just want to give you a quick pro tips video, and I'm going to use the in-class 10.2 practice to walk you through the pro tips for doing this particular mini quiz. Now, I want to start by saying before we even look at this classwork, the main thing that you might want to look for, heroes, is taking a look at the 10.2 warm-up, the warm-up that we did, where we talked about what it means for something to be positive, for it to be linear, for it to be strong, right? The different ways that we describe DOFs, right? So know how to describe DOFs. Not only using it, obviously, to describe a scatter plot or a regression line, but also use it as being able to express what each component of DOFs means, like we did in that warm-up that's up on Canvas. Now, to move to the main event, we're going to have to be able to read calculator or computer outputs for this particular quiz, okay? And we did this in class, but I want to make sure we're all clear about what to look for here. You'll notice the things I've already taken care of. R squared, the regular R squared value, is important. We need that. That is going to tell us the amount of variability in Y that is explained by the variable X, right? Remember that 1 minus R squared tells us what we can't explain. So if you look at this one, it says, for the part of the problem here for C, interpret the value of R squared in this context. Now, this context is talking about weed killer being used and the percentage of weeds that exist after the weed killer is used, so to speak. And I think it's actually saying the amount that we kill. So it's the amount of weeds or percent of weeds that have been killed by this weed killer. So when we look at that, what we're saying is that 97.2% of the variability in the percentage of weeds killed is explained by the amount of weed killer used. And that's a really, really good R squared for us. That means that 97.2% of what's going on with weeds dying is explained by the weed killer being used. On the other hand, what that also says is that only 2.8% of that variability is unexplained, so explained by some other variable. That's a really strong R squared. What that tells me is we'll never have causation, but we're pretty certain that this is what's leading to this, okay? So that's what we got for C, and that's what we got for that calculator output. For A, we're going to do this one together. It says, what is the equation of least squares? It doesn't matter when they say equation of least squares. What they're asking for you to do is use this calculator output to create your equation, and your equation will always start as y hat, so our predicted value of y. Then I like to put the intercept first because we tend to use a plus bx as our formula. But you could do mx plus b, both are acceptable. The intercept is always going to be under coefficient. So you want to first find just coefficient, regular coefficient, not SE coefficient, none of this crap. We don't care. Okay. It's under coefficient. And where it says variable, where it says constant, that is A. So here it's negative 20.5893. So negative 20.5893 is always our intercept. So the one right beneath coefficient, where it says constant, the constant coefficient, that's the same thing as your intercept. Versus the one coefficient that is marked in the number of teaspoons you use, in other words, x, the x variable, that's going to be your slope. So it's plus 24, whatever, 0.39 is what I'll write, x. Okay. And that is your equation for your least regression squared lines. And I will tell you, those three things are the most important things you will pull from a distribution readout like this. You don't really need the sum of squares unless they ask for it. The degrees of freedom are there. Don't worry about these, okay? Don't worry about these. You're just interested in this, the variable and coefficient, which tell you what the intercept is, followed by what the slope is, and then the R squared value. Okay, it says interpret the slope and y-intercept in context. I'm going to say this out loud because writing it would suck, especially in this space that I haven't left much for myself for. Excuse me. But the intercept of negative 20.5893 is the amount, or the percent, in this case, the percentage of weeds killed when no weed killer is used. So in other words, if it's negative in this context, that means 20.58% of weeds are growing instead of getting killed, right? We used no weed killer. The intercept will always be what happens when x is 0. So when x is 0 here, we've used no weed killer. That means that when there is no weed killer used, weeds, instead of dying by 20%, they actually gain 20% more, right? They gain 20.5893% more weeds when weed killer is not used at all. That's what the intercept would be. And the slope would be for every 1 teaspoon, right? Because teaspoon is what they use to measure it here. For every 1 teaspoon of weed killer used, 24.39 more percent of weeds are killed. Okay, for every one X, blank number of Ys will, whatever the context is. So in this case, for every 1 teaspoon of weed killer used, 24.39% more weeds are killed. Okay, we already went through C, but remember that when you talk about C, interpret R squared, you're always going to say the amount of variability in Y that is explained by X. So 97.2% of the variability in the percentage of weeds killed is explained by the amount of weed killer using, I just add in using the linear model, which is the most exact way you can say it. Okay, how do we find this? I love this one. Part D is very helpful. Find the value of the residual for a weed that had 3 teaspoons of weed killer and had 75% of weeds killed. Show your work, interpret the value. So first of all, residual equals actual minus predicted. My hint to you is, in this case, we're solving for the residual. So we found the actual, right? They gave it to us actually. And then we plug in our predicted. And we plug in our predicted doing the work I did over here. We used our equation and we just plugged in the value 3 for X. And that gives us 52.5894, and you plug that into our equation. You should get a residual of 22.4106. Be aware, I could give you a residual, okay, and give you a predicted value and ask you for an actual value. Or I could give you a residual and give you an X, and then you could plug that in to find the predicted, and then you could solve for an actual. That's a hint, Legends, on your quiz. I might ask you to solve for an actual value at a particular point using a residual and either a predicted value or the X component and the equation to find a predicted value. Remember to use under or over predicted when you interpret your residuals. The model under predicted the percent of weeds killed by 22.4106. Why? Because we have a positive residual. In other words, our residual is in such a place that things are worse off because of it. Okay. We expected a certain thing to be true on the actual line, and we undershot the amount of weeds killed. Actually, in a lot of ways, good news. We thought we would kill fewer weeds than we did, and it turns out that we actually killed more weeds than we thought we would. Okay. You can also kind of approximate what we would see for 3 by taking a look at our residuals graph to the right, but this is the exact way to get the answer. Okay, for part E, is a linear model appropriate for this data? No, look at this graph of residuals. It makes a parabola. That is a pattern, and that's what I say here. And then it says find the correlation coefficient for this data set, interpret it in context. The data show a strong positive correlation between teaspoons of weed killer and percent of weeds killed. Now let's take a look at the back page. Equally useful, I would say, for our quiz. Lydia and Bob are searching the internet. They're traveling the United States. They're looking from 1990 to 98 to see the number of commercial flights that are going on. Okay. Once again, we have a look. We only have and we only care about this line here. Okay. The top number being our intercept, the bottom number being our slope. The other thing we might want is the standard deviation, the standard error for the residuals. And we'll see if that comes up at all. We also have a graph of the residuals. For A, it says, is a linear model appropriate? Look at our residuals. They're all over the place. There's no pattern, and that's what I say. So therefore, yes, we can assume this is a linear because there's no pattern in the graph of residuals. What's the slope? Easy. It's right here. It's the number right below the intercept. So I wrote that down, and it says interpret it. As the year goes up by 1 year, 233.517 more commercial aircraft are flown, right? The slope is saying how much Y will change and in what direction for every 1 of X. For C, what is the value of the intercept? Again, it's right here, right above the slope, 2,939.93. What does that mean in context? Well, here you can see I underline it. It says the year 1990 was recorded as 0. So for this distribution, right, for this scatter plot, 0 is the number of flights in 1990. This means that at X equals 0 in 1990, there were 2,939.93 flights flown. What's the residual for the number of commercial aircraft flying in 92? Well, if you go to 1992, which is 90 is 0, 91 is 91, and then 92, you go up. That's our graph of residuals, so we can literally just read our graph, right? And that's where Y equals 40. Okay. The residual difference, I should say, is 40. And then E, would it be reasonable to use the fitted regression equation to predict the number of commercial flights in 2019? You should have said no, because that's extrapolation. We only have data between 1990 and 1998. Anything beyond or before that is beyond what we've actually gathered data for. So we cannot extrapolate. We have to only predict. I hope this has been helpful. I will tell you right now, if you look at this and go through this and feel good about reading the calculator outputs, and then if you look over your warm-up from class as well, and know how to explain, again, what is strength in context, what is position in context, what is direction in context, what is slope in context, what is R squared in context. All of these contextual things are very important things. And again, linearity, right? And what are outliers or no outliers meaning in context? Then you are absolutely ready. And then be aware of the little trick I was telling you about, where if I give you a residual and I give you an X value to solve for a predicted value using an equation, right, a regressions equation, you should be able to solve for an actual data point. All right, legends, you've been amazing. I'm sorry to throw this out so late, but you are ready. You've got this. And this is Mr. Mays signing off.